Hi everyone, welcome back. We're going to continue with part two of the alloys course. If you remember, we discussed briefly about solutions and how alloys are also solid solutions. So also we discussed about some of the classical alloys, how alloys could be made as a solid solution. If you don't know what I'm talking about, please check our previous videos. I will put the link in the description. And also you can go to the channel page and look for playlist for material science and other courses to see what we're talking about. But solutions and alloys part one, you need that to be able to follow this one, okay? So we're going to continue with alloys. If you remember, we ended up in understanding water and sugar as a solution, and then how alloys are basically solutions just like sugar and water, but in solid state with having a metal as one of their main parts. And so from a phase diagram of a solution, we want to understand the phase diagram of an alloy, which is a metal-based solution, and that is steel, which is an iron carbon alloy. And as you can see here in the slide, their phase diagram is really different. So in this course, we want to take a deeper dive into phase diagrams and kind of break them apart so we can understand phase diagrams and use it to our advantage so we can understand alloys. Why do we need to understand phase diagrams? Is the same like sugar, example of sugar and water. You exactly will know once you understand phase diagram of alloys when which phase will be formed, and depending on the composition, like how much of the materials you're adding to each other with respect to composition, with respect to temperature, at what temperature, at which composition, you get what type of solution with what kind of property. And we want to understand it for alloys, including steel, which is like the main part of our discussion. Okay, so to be able to take a deeper dive into phase diagrams, I'll bring you this slide. This shows two main categories of phase diagrams, and phase diagrams are supposed to show us possible phases that are stable at different temperatures and compositions. So we have two main categories of phase diagrams. First one we call complete solubility, is for materials and elements that will completely dissolve into each other. So no matter how much of each part you're adding to make a solution, you still make a solution and nothing will crystallize out. You will never get super saturated. So it will always, you can mix all the elements and materials in whatever fraction that you want, and you still get your complete solution. So that's one type of an alloy or solution, that you have complete solubility. And the other one is partial solubility, that is here. This partial solubility, as you can see, phase diagram of partial soluble materials is very different than complete solubility. And the partial solubility, as the name gives it away, the elements that you have, the materials that you have, they have partial solubility, meaning that you cannot dissolve whatever amount that you want to your parent, to your host element, and still get the same phase. The phases will change because solubility is changing. So you have solubility up to a certain limit. For example, in the case of magnesium and silicon, you cannot add silicon to magnesium in whatever amount that you want and still get the same phase. If you, up to some extent, you can dissolve silicon into magnesium, and after that, you will get different phases forming depending on how much silicon you're adding. But in case of copper and nickel with complete solubility, no matter how much nickel you're adding to a copper, you still get your solid solution. Solid solution will still be there, but at a different composition of nickel, but still it's a solid solution. But for limited or partial solubility, you don't get a one-phase solid solution by adding whatever amount of silicon, for example, that you want. The solid solution that you can make is limited, exactly like sugar and water. You cannot add infinite amount of sugar into your water and still get a solution. After some point, you will pass the a solubility limit, and then you cannot dissolve more sugar into water. It's the same thing for partial solubility of magnesium and silicon. After some point, which we will dive into it and we'll know how to read them, but for now, it's just enough to know that it's just sugar and just like sugar and water. You cannot add this amount of silicon into magnesium. At some point, you cannot add any more to that to get a solid solution. So this is what we need. We have partial solubility and complete solubility. As you can see, complete solubility phase diagrams are a bit simpler. So we start with understanding the phase diagrams of complete solubility for materials that have this kind of property, and then we will dive into partial solubility after that. So if you look at, now I'm zooming a bit more on complete solubility. If you look at complete solubility, we first, because it's a phase diagram, we call this a phase diagram, we need to first to be able to identify phases that are there. So let's begin with reading our phase diagram. Phase diagram here, just like the sugar here, is just temperature. It's starting for this kind of a material, it's starting from 1000 degrees Celsius to 1600. Usually phase diagrams are like cropped like this because for some certain temperatures within some certain range, because anything below or above is not really interesting or applicable. That's why they're sometimes cropped, so you don't see 25 degrees or 0 degrees. It starts with 1000 because that's the region of our interest. That's why we do that. Otherwise, you can also do it and bring it down. So that's our temperature, which shows which phases we get at what temperature. And here, you read here is that composition with respect to WT percent is weight percent, with respect to weight percent of nickel. What it means is that here is 0% nickel, 100% copper. When it said with respect to nickel, it means that here nickel is 0 and here nickel is 100. So when here nickel is 0, you have 100% copper. And here when nickel is 100%, you have 0% copper, obviously. So if here we have 100% copper, we are talking about here. If here we have 100% copper and 0% nickel, then this point, which our phase diagram is crossing at this point at 0% nickel and 100% copper, we have everything we have is now in copper. Then here is the melting temperature of copper. So at 1085, crossing this line is the melting temperature of our copper. We have pure copper. Going all the way to the other side of the phase diagram here that we have 100% nickel, then in this point, this is the melting temperature of nickel. That is 1455. So reading the phase diagram, we can now be pinpointed two melting points of pure copper and pure nickel. So that's the first information that we received, that we taken out from these phase diagrams for our advantage, so that we understand the behavior of material just by looking at these phase diagrams, and you know a lot about the property of your materials and your alloy. So that's first thing, melting temperature. Now, if you look at here, it says liquid, obviously, because when we increase the temperature and we pass this point, we went from solid phase, here was solid, and we stepped into liquid phase at this point, which was the melting temperature of copper. Same here, from solid phase and 100% nickel, when you pass this point, we've entered the liquid phase, therefore it was melting temperature of nickel. So we have liquid region, which all this area above this line, we call liquid, it is liquid range, and anything below this line is our solid region. it's the region where we have the solid phase. So we now identify two phases, one above this line, which is the liquid region, and one below this line, that is the solid region. And whatever that is in between in this region, that looks like an airfoil, like for an airplane wings, look like a cross section of an airfoil. Therefore, whatever that we have in this region is a solid state plus liquid. So in this airfoil shaped region, we have two phases existing at the same time, liquid and solid, as you can see here noted here. So we have solid and liquid being present at the same time. Above this region, we have only liquid, and below this region, we only have solid. The line, this line, that separates the liquid from this two-phase region, we call liquidus line. So the line that has an interface between liquid and this two-phase region, liquid plus solid, we call liquidus line, and the line that has an interface with your solid, we call solidus line. So just to remember it, your liquidus line need to have an interface, at least one interface with the liquid, then you call it liquidus line. And if your this borderline has an interface with your solid, then you call it a solidus line. Below solidus line, we have solid. Above liquidus line, we have liquid. And between them in this two-phase region, we have liquid plus solid. So that's how it looks like. If you have, let's say, 3 melting pots, I'm drawing 3 melting pots. And then imagine you have, let's say, liquid in it. So liquid for us would be this. You have liquid inside it. So we are, let's say, at 1500 degrees. At 1500 degrees, it's really liquid. That's how your liquid is looking like. When you enter from the liquid into the two-phase region, then it is telling you that if you're coming from liquid, you're cooling down. You're cooling down. You're coming down from liquid to your solid. It tells you that you've entered the two-phase region, liquid plus solid. Therefore, in this region, you would have liquid and some solid. Now, the green is now a bit of solid that is forming in your liquid, and then the rest is still liquid. So that is how the two-phase region in this airfoil shaped region would look like in your melting pot. In the liquid phase, it will be just a liquid, and then you get some solid particles in this two-phase region growing. And when you are passing all the way here to the solid region, that now everything is solid, then you should have everything in solid. That's how it would look like. So this is the region that you have all solid. So you start from liquid, then you enter the two-phase region, solid plus liquid, and then you enter the solid phase, and then you get all solid. So it doesn't matter where you are. So here it changes with compositions. For example, this is now with 80% nickel. If you have at 80% nickel, for example, if you start at this temperature, then when you are coming down like that, imagine this is a straight line. When you're coming down, it exactly works like here. So as long for 80% nickel, as long as you are in these regions, all these dots, then you get a liquid, just like that. Once you enter for 80% nickel, once you enter in this region, which is, let's say, roughly 1400 degrees, then you've entered the two-phase region, and you get solid plus liquid. And once you go down, you cool down furthermore, let's say at 1250 in here, at this composition, then you get all solid solution, which would look like all the green. The same goes for here. So if you start here for an alloy that has 10% nickel, here it has 10% nickel. When you start here, as long as you are above the liquidus line, any temperature, let's say at 1200 degrees, what you get the melt. Once you enter here, then you get solid plus liquid, which would look like this. But as you can see, the temperatures are different. And once you're coming down, for example, to this one, then you get solid. But the trend that you see is that all these, the transition temperature is going higher. What it's telling us is that as um, if you add more nickel to your alloy, then the two-phase, the temperature for a two-phase region also is going up. So for example, if you have, that's what it means for an alloy, for a couple nickel alloy that has 10% nickel, the average temperature that you get two-phase together, solid and liquid, is here, is about 1150, let's say roughly, okay? But once you add, instead of 10%, 50% that you come here, then the temperature has raised from 1150 that was here for the two-phase region. Now it's, let's say, 1250 for these two-phase region, the average temperature there. And once you go from 50% to 80%, this has increased, let's say, to 1350. So look how this is useful. It is telling you if you add more nickel, yes, you can dissolve nickel into copper into whatever amount and fracture that you want. But bear in mind, this phase diagram is telling us, bear in mind that if you add more nickel to your copper, yes, you still get a solution that is one phase solution, everything will be dissolved, but the temperature of this two-phase region will increase as you're adding nickel. So if you have it at 10% at 1150, then that two-phase region will, the temperature that you will get it will increase from 1150 to 1350. So that's how we are reading the two-phase, a complete solubility of a binary alloy, which includes two alloys, copper and nickel. So this is about there are more to derive from phase diagrams like that, but I will stop right here to go also to talk about a bit how to read phase diagrams for partial solubility, and then we come back to see what else we can derive from phase diagrams like that. Okay, so bear in mind that they can be more, but for now we can read phase diagram to see what phases are forming at which temperature and how these phases are forming once you're cooling down. So that's quite a bit of information. Now let's go to phase diagrams for partial solubility. Partial solubility, as you can see, it's different than complete solubility, but in some ways they are the same. And that is that you have a liquid phase also, that is here, all this region is your liquid phase, and also you have your solid phase, that is all this area. This is your solid phase, this is also your solid phase, and this is your solid phase. And the red or purple is these regions are where you have two phases being present at the same time, just like the complete solubility. We have it here, and you see liquid also being present here and liquid present here, and plus a solid, which is called beta and alpha in this case. So in these cases, um, they are the same, that they have a liquid, the partial solubility phase diagrams, and they have a solid phase. So first, let's see if we can apply what we learned so far onto this phase diagram, but for partial solubility. First thing that we learn is that, yes, I identified the liquid region and liquid phase and liquidus line. Liquidus line always has a border with your liquid. So our liquidus line in this case is this line. This line that I'm drawing on, this is our liquidus line. Above this, we have liquid, as noted here. And our solidus line, which has an interface, a shared border with solid, is now this one. So this is our solidus line. And as you can see, everything below it, this is a solid, and also alpha is solid. Everything below it is solid, so it has a border with solid, and everything in between is a two-phase region. Here we have alpha plus liquid, and we have beta plus liquid. So that's the first thing that we learned on complete solubility and that we can apply here. Now we know where liquid is and where solid is and where the other regions are. Now let's see with the example of this melting pot, let's see if we can imagine our melting pot to see what we can expect to take place and to form in a partial solubility example. So in a partial solubility example, it starts, for example, for an alloy that has about, say, maybe 7% silver. Again, look at here, it says composition with respect to silver. And then therefore here is 100% silver and here is 100% copper. This is maybe about 7% silver. So what is it telling us? That at 7% silver for a copper silver alloy, let's heat it up all the way to 1000 degrees. This phase diagram tells us that, okay, at 1000 degrees for this composition, we are in the liquid region. Therefore, we need to have a melting pot all filled with liquid. So nothing is forming yet. But let's try to cool it down. As we are cooling it down, then we enter this region that is a solid plus liquid. Therefore, in here, we need to have two phases being present. If you look at here, we have liquid and we have alpha, because in this region tells you what kind of phases are forming. So this region has two borders, one with liquid, of course, and the other one, this line with alpha. Therefore, is alpha plus liquid. This one has two borders. One is this one with liquid, and the other one is our solidus line with beta. Therefore, this region is also made from beta plus liquid. So therefore, when you're here, you have alpha, which is one at your left and the other one at your right. So it's alpha plus liquid. And once you're here, you want to cool it down further. So while you're cooling it down, as you can see here, we've exited alpha plus liquid. We exited that region. It means that once you exit that region, it means that you should not have that anymore in your pot. And so, okay, so that needs to go. What needs to come in? It says at this temperature and composition, then you enter into alpha phase, which is your solid solution. So partial solubility, now we can define it. Partial solubility, we have these solutions. So this alpha is a solid solution, and we discussed before that solutions are single phase. So alpha is a single phase solid solution, but with partial solubility. With partial solubility. That's its solubility limit. And also for beta, which is another solid solution, that's its limit. exactly like sugar and water, that you had a limit for solubility, and after that you cannot add anymore. It's the same thing. So for a copper alloy, up to this amount, comparing to, depending on at which temperature we are talking about, but this is your limit. If you go beyond it, you cannot dissolve more silver in copper. The same for this region. It shows that, okay, this is a silver and we want to add a bit of copper to it. Yes, you can add copper to it, and in this way, you add copper to it, right? Because here is 100% copper, here's 100% silver. Yes, you can add some copper, but up to some certain limit. That was our limit. And if you add more, then it won't be dissolved. More of that won't be dissolved, and you get a two-phase in between, alpha plus beta. Because you cannot have a single region that you dissolve all of them, no matter at which composition. No, if you have 100% copper, you can add, say, up to 10% silver to it, and after that, you cannot add more, so you cannot have only alpha, then beta also comes out. The same on the other side. If you have 100% silver and you add, yes, you can add a small amount of copper, but if you add more, it won't be dissolved to it, and alpha appears because alpha is rich. Alpha is rich in copper, has a lot of copper, and beta phase is rich in silver. It has a lot of silver. So if you have a lot of silver, you add a bit of copper to it. Yes, you can add to some extent, but if you add more, alpha appears that is rich in copper, and vice versa. That's why in here we have alpha plus beta, because you cannot have only alpha and only beta because of the partial or limited solubility. Okay, so now we are, see if I can, yes. So now we have exited the alpha plus liquid, which was this, and now we have entered this. So the liquid should disappear, and we should have only alpha at this composition, 7% silver, and at this temperature, roughly 800 degrees. It tells us because we are in alpha region, we should have alpha. And look at this image, all alpha in solid form. So these alphas that we had here, they will be there in here, and the liquid, the yellow, the liquid will also turn into alpha. Because in this region, first we had liquid, and then liquid turned into alpha plus liquid. We are now cooling in this direction. We are cooling. So that's what happened. We first had liquid in here, and then we cooled it down. It turned into alpha plus liquid, and then we cooled it down further. It came down and we entered this region, which was only alpha. And then from here, we are cooling down even more to this one. And you are exiting the alpha region, meaning that that should disappear. The only alpha phase should disappear and something else should form. What should form? Alpha, we are in the region of alpha plus beta. So beta will crystallize out of alpha because it was supersaturated. You remember? So if you do not get it now, you need to watch the solution video because there I discuss what is crystallizing out. Okay, so I'm not going to that, but watch that video to be able to understand this. So here we have some amount of silver dissolved in copper as alpha, just like sugar dissolving water at high temperature. But once we cooled it down, that amount of silver couldn't stay in alpha at a cooler temperature. So when we cooled it down, then the excess amount of silver, which was dissolved in copper as alpha, is crystallizing out, and this phase diagram is telling you that the excess silver will crystallize out as beta. So you get alpha plus beta. That will look like that. From this alpha, beta crystallized out, and then you get this image. That's what's happening for phase diagram. So it's also telling you, therefore, alpha, when we pulled it down, turn into alpha plus beta. Alpha, of course, is copper rich, and this is silver rich. So that's the kind of phase transformation that happened. So for this amount of copper, for like 7% amount of copper, at 1000 degrees Celsius, we had liquid, and let's say at 870 degrees, we had this phase, and then at 800, we had alpha, and then let's say at 450, we got alpha plus beta. What it tells you, very useful information. It is telling you, hey, if you have copper, you added 7% of silver to it, you mixed it, made a one phase, let's say, made a solution, no matter what kind, how many phases. If you keep this mix at 1000 degrees, they will be all liquid. If you bring it to 870 degrees, they will be liquid with some alpha. What is alpha? A copper-rich alloy with some silver in it. If you cool it down a bit more to 800 degrees, let's say, just look at it, just 70 degrees. If you change it by 70 degrees, cool it down more, you're not going to get any liquid. You will get all alpha, all an alloy that is really very rich in copper with some amount of silver in one phase at 800 degrees. But if you cool it down to 450, you're not going to get one phase anymore. The excess amount of silver that was dissolved in copper cannot be dissolved anymore. So it will crystallize out as what? As beta. How do we know? This phase diagram is telling us. This phase diagram is telling us that in this region, on the left side, you have alpha. That's one of your borders. And on the right side is your beta, your second border. So whatever that is in between these borders, they are your phases. So we have alpha plus beta. Therefore, what's coming out? Beta is coming out. If it was a different phase here, like for example, if it was just silver, instead of beta, it was just silver, like elemental silver, then here we would have alpha plus silver, because on the right side you have silver, right? So that's how we determine phases using a phase diagram. It can happen to anywhere. So I'll bring the ruler. I'm gonna do two more lines. One here and one here. Okay. So still PowerPoint is not that smart when you erase things. Okay. Yeah. One line is disappeared, so I'll do it once more. So we want to practice with these two. Now we know what's happening here. Let's go to 40%. So an alloy that has 40% silver and 60% copper, if you're at 1000 degrees compared to this, you still have liquid. If you are at this temperature, well, for this alloy, for 7%, you have some solid because you're in this region, your region of alpha plus liquid. So you have solid, but for this alloy with 40% in here, you're still in liquid region. So you still have this. Look, that's the difference. That's the kind of information that phase diagrams tell you. For 7% silver and copper, at this temperature, you get solid alpha plus liquid that looks like that. But if you add the silver from 7% to 40%, then at that temperature, you still have liquid, okay? So what about 80%? 80% at this temperature, it's still liquid. At this temperature, also, just like that, it's still liquid. we come down to here for, whoa, for this alloy, 7%. Maybe it's misleading here. So for this alloy, for 7%, we have pure alpha, single phase alpha, which is a copper-rich alloy with some amount of silver in it in here. That is alpha. For this alloy at this temperature, we don't have single phase alpha. Look where we are. We are in the two-phase region of alpha plus liquid. So at this temperature, for this alloy, we have a composition that looks like this. That looks like this because it's alpha plus liquid. Well, what about this alloy with 80% silver? Well, for 80% silver at this temperature, it's beta plus liquid. So you would have something that looks like that, but instead of alpha, it would be beta for this alloy with 80% silver. Okay, so that's how they differ. Like this alloy with 80% beta, there's no alpha forming at this temperature. It will be only beta. But look at this alloy. Once it goes from beta plus liquid to this temperature, the beta plus liquid should turn into alpha plus beta. And for here, alpha plus liquid in here should turn into alpha plus beta. So I'll call this alloy 1, I call this alloy 2, and I call this alloy 3. But for alloy 1, we draw what kind of phases are forming. For alloy 2, that is it. So we started from liquid, this point. The second point was also liquid. The third point was alpha plus liquid. And the fourth point was alpha plus beta. So in this transition, that's what we get. For alloy number 3, first point is liquid. Second point is also liquid. Third point is beta plus liquid. And fourth point is alpha plus beta, right? We can also put it, also do for one, so one more time, so that's in its perspective. So at point 1 we had liquid, point 2 we had alpha plus liquid, point 3 we had alpha, and then last point we had alpha plus beta. So look, they are the same in terms of how many phases and what kind of phases are available at lower temperatures. But look how the phase transition is different. Liquid, liquid, alpha plus liquid, 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 beta plus liquid. And this one, liquid, alpha plus liquid, and alpha. So at different temperatures, you can get different phases using the phase diagram. It tells you that with respect to composition at temperature, what kind of phases you can get. I think that's enough for now. This is about how to read partial solubility phase diagrams and complete phase diagrams to see what kind of phases at which temperature can form. Next time, we're going to talk about the lever rule and quantifying the amount of the compositions and phase fractions to see what is the phase fraction when we say we have alpha plus beta, how much alpha and how much beta we're going to discuss, and also within alpha, how to calculate how many copper, when we say, for example, alpha is copper rich, with a lot of copper and a bit of silver, how much exactly, so we can quantify it. So next time we're going to continue with the lever rule and defining and calculating the composition and phase fractions, going to steel, and then trying to apply it to steel. So because it's all about understanding steel and a phase diagram of it and also other alloys, then we can finalize the whole course about alloys. I see you next time. Bye.